Another electrophilic substitution reaction of benzene is Friedel-Crafts reaction. Now Friedel-Crafts reaction is of two types: Friedel-Crafts alkylation reaction and Friedel-Crafts acylation reaction. In Friedel-Crafts alkylation reaction, an alkyl group is entered in benzene ring, and in acylation reaction an acyl group or acetyl group can be entered in benzene ring. So in alkylation, FC, Friedel-Crafts alkylation reaction, let us see what happens. The alkyl group means the methyl, either it can be methyl or ethyl or propyl or tertiary butyl, any of them. So if we want to see this methyl group into the benzene ring, here we take benzene and this group has to be entered into this benzene ring to make this compound benzene, and here CH3, and this compound is known as toluene. This compound is known as toluene. Now how can we make this? We have to take this alkyl group and an halide of this alkyl group. That means halide means you can take CH3Cl or CH3Br or CH3I. Now we take here the CH3Br, and in presence of, you can keep CH3Br, or you can also take CH3Cl, methyl chloride, in presence of anhydrous AlCl3. Okay, if you take this, if you treat benzene with methyl chloride in presence of anhydrous aluminium chloride, then toluene will be formed. The reaction mechanism is very simple. As aluminium chloride, you know that aluminium, electronic configuration of aluminium is, the atomic number of aluminium is 13, that is 1:2, 2:2, 2p6. 1:2, 2:2, 2p6, that means configuration of neon, and after then 1:2, 2:2, 2p6 means 10, and then 3s2 and then 3p1, that is the electronic configuration, that is the outermost shell electronic configuration of aluminium. Okay, here in 3s orbital 2 electrons are present, and in 3p orbitals only 1 electron is present. Now if 1 electron from 3s shifts to 3p orbitals, then the number of unpaired electrons here is 3, 1 in 3s orbital and 2 in 3p orbitals. So aluminum can make 3 bonds with 3 chlorine to form LCl3. Now after formation of this all unpaired electrons get paired, still this pz orbital remains vacant. So in aluminum chloride, the central atom aluminum has a vacant pz orbital. Now if anyone can give a paired electron, that means there are lone paired electron or negative charge to aluminum chloride, aluminum can accept that paired electrons and can accommodate it in its vacant pz orbital. So we can say aluminum chloride is a lone pair acceptor or electron pair acceptor, and you know which can accept lone pair or electron pair is called a Lewis acid. So aluminum chloride is a Lewis acid. Now let's see how the reaction occurs. When you add CH3Cl methyl chloride in benzene, the reaction can occur but in very slow rate. Why the reaction would occur? As chlorine is more electronegative than carbon, the bond pair electrons, it will pull the bond pair electrons, and at the same time the CH3 group, methyl group, methyl group has plus I inductive effect. Plus I inductive effect means the tendency to push the bond pair electrons to the other end. Okay, so these two facts actually make a charge separation in CH3Cl molecule. Here on carbon some partial positive charge will be there, and in chlorine some negative charge will be there. So an electrophilic center has been generated. So pi electrons can attack to this carbon. To actually increase the rate of the reaction, a catalyst is used, which is aluminum chloride. Now this aluminum chloride is a Lewis acid. It can accept the lone pair electron from chlorine. Chlorine has a lone pair electron, so chlorine can make a coordinate bond with this aluminum and aluminum chloride. So when a coordinate bond is formed, chlorine cannot make 2 bonds at a time, so this bond has to be broken. Okay, so chlorine These bond pair electrons will go away with chlorine, and CH3 group will have a full positive charge. That means a methyl ion, CH3 plus ion will be formed, and here along with LCl4 minus, as the bond pair electrons go away with chlorine, so aluminum will have or the excess paired electrons comes in aluminum, so aluminum will have a negative charge. Aluminum LCl4 minus ion will be formed. Now this attack will be very easy. As this CH3 plus ion is formed, the production of this carbocation will make the electrophilic attack. That means pi electrons now will come faster to attack or to make a bond with this carbon of CH3 group. So what will be formed as the bond is broken from this carbon? So here a positive charge will be formed, and CH3 will go above the plane, and hydrogen was already there which will go below the plane. Now what happens? Hydrogen gives its bond pair electrons and removed as H plus ion. So here H plus ion is removed, and again benzene is formed with CH3 instead of hydrogen, but hydrogen atom is there. Now hydrogen is replaced by CH3 group, now toluene is formed, and this H plus, and here LCl4 minus ion is also formed, H plus and this Cl minus ion will combine to form HCl, and again LCl3 will remain unchanged. So aluminum chloride just acts as a Lewis acid in the reaction, in the Friedel-Crafts alkylation reaction. Okay, so this is the simple mechanism of Friedel-Crafts alkylation reaction. We need to take CH3Cl or any alkyl group you want to add to the benzene ring, its halide, the halide of that alkyl group, along with anhydrous LCl3, where anhydrous LCl3 acts as a Lewis acid. At the very beginning, what happens? The chlorine, or you can take bromine or iodine, whatever. So this chlorine, which was bonded with CH2 group, that is with the alkyl group, make a coordinate bond with aluminum chloride and get separated to form LCl4 minus ion, and as that is why CH3 plus ion is formed. Here this carbon was carrying a partial positive charge, but here a whole positive charge is on this carbon. So rate of attack by the pi electrons of benzene that must be faster here than in absence of LCl3. Okay, so that is why we can say aluminum chloride acts as a Lewis acid in Friedel-Crafts alkylation reaction. Now let's consider some other reaction which is also Friedel-Crafts reaction, Friedel-Crafts alkylation reaction.